Hello everyone and welcome to a new episode of All Things IDA. Today I'm going to be introducing you to processor module development. Luckily I have a simple virtual machine that we can use to do this introduction. I'm gonna be continuing the work from last time when we discussed file loaders for the cat-bird files. Now we're gonna implement the virtual machine as a processor module in IDA so that we can complement the loader. So once the file is loaded, the processor module kicks in and we have a nice disassembly of that simple virtual machine. With that, let's get started. The topic of processor module development is a bit complicated. There's not enough documentation, and so personally I'm grateful to have had the opportunity to work at Hexrays and get the chance to develop a processor module in C++, and then had the chance as well to design the Python interfaces so you can implement processor modules in Python. I'm not going to be talking how to implement processor module in Python right now, but hopefully in the future we can approach that. So to begin with, like plugins and file loaders, there will be a symbol that we need to export when we are developing the processor modules. And it starts with the LPH symbol of type processor_t. At a high level, these are the biggest attributes we should be defining. Flags and related attributes, so just like a bunch of constants stored together that will dictate the behavior of the processor module. That also a processor module ID is a numeric value. Then we have processor names, so how the display name, what's the processor name ID as well, just like 8-character code string we can use with other APIs to programmatically select the processor module. So this will link back to the loader code that we discussed in a previous video, where the loader will select the processor module and it selects processor module by its name ID. So it goes here in the processor names. We have the assembler definition where the IDA kernel does not hardcode any assembler syntax. So let's say we're reversing stuff for x86, x64. We see assembly syntax for the Microsoft micro assembler MASM. So the keywords such as entp, sub, proc, seg, offset, dd, db, all those strings are not hard-coded in the IDA kernel. They live in the processor module, in the PC processor module. So similarly, if we're gonna design our own processor module, we have to provide IDA with an assembler definition. We can provide multiple assemblers, and in the UI in IDA, we can go to the options and select the assembler syntax we want. So that's something that the kernel will use to help it output certain things. Then we have notification routine or a mechanism that will let the processor module handle essential events, such as when the kernel wants to decode an instruction, it will call our notification routine, which will handle multiple events, including instruction decoding, instruction emulation, certain questions that IDA can ask or the kernel can ask or the user can ask via an API call. As well, part of making a processor module require us to also introduce the registers and their names into IDA. And so as well, we'll have a table of register names as a string table and the corresponding enum IDs and symbolic constants. And same goes for the instructions. We will have to introduce all the supported instructions as well. And this topic I touch upon from the user perspective, not developing a processor module before, but from using a processor module. So if you catch my previous video here entitled IDA Python Generating Assembly Line and Instruction Decoding, I do talk about how we can use a processor module. So today we're going to be implementing a processor module. So we see behind the scenes why and how when we used the instruction decoding and generating this assembly line, how that worked Today we'll see the behind the scenes how those things work. So I'm gonna switch to the source code and start talking about every attribute one by one so that you slowly formulate the big picture. So going to the source code of the PigletVM processor module, and our entry point is the processor definition here and the exported LPH symbol. So this symbol should be exported, and this whole process is way easy if you use ida.cmake. So I have set up an ida.cmake for both the file loader and the processor module, and this is the simple section here for the processor module. By doing that and using ida.cmake, that symbol, the LPH symbol, will be automatically exported for us. So our first entry point here, let's go to that structure and start talking about the first thing here, which are the flags and related attributes. So we have to specify version. We've seen that is a common occurrence when we're working with a loader as well as a plugin. So for example here, for the loader LDSC symbol, the first thing is the version, and then flags, and then callbacks. So it's very similar. So the more you program for IDA, the more things become familiar. So we have the version, we have the processor ID, and here the processor ID, we should be careful on how we select. So there's a convention. First, we have the processor ID is hard-coded for the things that IDA supports. These are stuff that ship with IDA, either closed source or not. In fact, the SDK has a lot of open source processor modules we can learn from. And so we shouldn't be using any of those numbers. And if we're developing our own, we should have numbers above 8000 hex. So this is what I did here. I defined my own ID to be above 8000 hex. Then we have a bunch of flags as well we can look at. Flags 1, flags 2. We have the number of bits for the code segments. So number of bits per byte, we have 8 by default, and for the data or non-code as well, 8 bits per byte. So that's what I did here, 8. Then we have the processor names. The processor names, we have two. We have the short names and the long names. So we have short processor names. These are the names we can use with the set processor module we used here, API in the loader. So here set processor type, we are passing the processor ID or processor name, the short name. So the short names is an array of short names, and long names as well is descriptive. Then we have the assembler definition. For the assembler definition, the IDA kernel does not hardcode stuff such as proc, and p, seg, offset, db, dw, etc. Since they're not hard-coded, depending on the loaded processor module, IDA will consult the processor_t structure, go to the assembler field. From the assembler field, it will get all the text it needs to emit headers, footers, and certain syntax. The processor module definition accepts an array of assemblers, so that will dictate different assembler syntax for the same processor module. And this is evident in IDA. For example, if we run IDA like that, by default here it's gonna be the PC processor module. If I go here, the target assembler, this is coming from the ASM_T list that we are specifying in the processor definition. And those will dictate how the syntax looks like. Now, since in my example for the PigletVM, I don't intend to reassemble anything, we can really be very liberal in the definitions that we can put in the ASMT. So the ASMT, for example, also has a flag. And so it's a combination of flags. It will have the assembler name, help screen if there is, header lines, or org directive. And so here hexrace tries to be generic. So since IDA handles multiple architectures and so on, the kernel, the IDA kernel, should be as generic as possible. So this ASM_T structure tries to capture a generic and broad set of definitions that may or may not be applicable in your case, but it tries to be as generic as possible. So that's what we're dealing with. String literal delimiter, the string for displaying ASCII string literals, bytes, words, the dupe, the duplicate keyword or for the array, BSS, the directive, EQ, equivalence, current IP, for example, $sign on the MASM, and different stuff, for example, the size of keyword, shift left, and so on. So if we look at my assembler here, I specified a single assembler table, so here, and I put as much as is applicable in my case. Some stuff I decided to keep as they would look in x64 or x86, for example. So really here, since I'm not following a standard and very much used virtual machine, this is a toy virtual machine, so it's fine. Whatever display makes us feel good, I just put some field values here. So as you can see here, I left so many things as null since they don't apply. Even this and or, we won't even see them, but just I filled them in. So this is the assembler table, and that what will also, as I said, affect the display in IDA, since the kernel does not hardcode anything. So after the assembler, we have the notification routine. The notification routine historically was in fact a routine, but right now it's a bit of a hack to maintain backwards compatibility. So the notify used to really be like a hook notification point, a callback that receives user data, event ID, and the variadic list of arguments. In modern IDA, since recent refactor, probably around IDA 7 or so, the notify routine now has a single purpose, is to return a new instance of the PigletVM, for example, or whatever we subclass from proc mode. So the notify routine that we set in the processor definition should simply return a new instance of our subclass. So we should subclass proc mode, and proc mode, if we look at the definition, it has as well, it subclasses different helper classes, in particular the event listener. And because of that, the event listener has a pure virtual method called onEvent. And that's where we put the logic of the notify function. So back in the days, the notify function would contain the whole logic, but now we are going through this dance where the notify that we link in the processor definition, it should return an instance of a proc mode. The proc mode instance will override the on event, and then inside the on event we would put what we used to put directly in the notification. So if you look at the older IDA SDKs, it's gonna look different. So here, since I'm targeting the latest IDA, I took the opportunity just to discuss a bit the historic changes. So for the notify functions then, as well, you will see this boilerplate code in the processor module examples. And the sole responsibility for this notify routine that we're linking here in the processor definition, its sole job is to return a new instance. And this is something we can use. So set module is the one that is returning a new instance. So that's the notify. Now, if I show you what's inside the on event, I'm gonna talk in details about those, but we receive a message ID and a variadic list of arguments. And we have to handle a set of events. And we'll see how this whole picture comes all together. But for now, this is the notify part of the processor definition. After the notification routine, we have register names and other definitions. So let's quickly jump to the register names. So the register names is also supposed to be a string table with all the registers that we support. Now, it's best as well to have another enum that is parallel to that string table. And this is something as well that we discussed in the video here, generating the assembly lines, where when we are decoding an instruction, we might get its operands, and its operands, we will have a register field, for example, and the register will not be a string, it will be an ID. And that ID is what we define here. For example, not all register IDs are given in the SDK. So here I'm repeating myself, I've spoken about this topic before. If we look at intel.hpp, this is coming from the source code of the processor module for the PC processor module. And here, for example, this enum here, reg numbers, these are exactly what I am defining in my own processor module, this. So intel.hpp is given to us as a partial source code of the PC processor module, which is closed source. We don't have the full source code of the processor module. So if I try to go to IDA SDK and go to the modules folder, these are the example processor modules that come with the SDK. And we don't have the processor module for PC, but we have other stuff. So that's why we were given like just one header file of the source code just to help us at least decode and make sense of x86 instructions. So for the registers, we have to specify a table, a string table with register names and the corresponding enums. Then we'll specify the enums designating the first register and the last register. So as well, don't first here it wants the segment register and the last segment register. So we just tell it, and as well you can follow the examples, and just you will notice most of the examples we see use the same stuff. So I'm using here the word v for, since the code segment and data segment don't really apply, and the v here notates virtual registers just to satisfy the IDA kernel requirements, how the IDA SDK works and so on. So the registers that make sense here in this processor module are the instruction pointer, stack pointer, and a special register for this virtual machine that holds the result. As well, we can completely get rid of most of those. It's up to us how we want to design our processor module for IDA. So I just introduce them, although we will not necessarily see them in this implementation of the processor module. We won't see them anywhere. So we just keep on filling in the requirements of the processor definition, which is a big structure. So we cover the assembler. Here the events, we're going to talk about the events, the notify routine, a bunch of helper methods, and the register table, number of registers. So we have to tell IDA how big is this register array. So this register array is as big as the same elements here in the enum, and also that will dictate the size of that registers table. And then can go back, continue. So we have other stuff. So here, first segment register, so I use the virtual register. Last segment register, size of segment register in bytes. So here it doesn't, I say it doesn't apply. And the number of CS registers, so what is the ID? This is a virtual register ID, and this is a virtual register ID. We can also hard code some stuff, array of typical code start sequence. I didn't specify it. Byte sequence for return instructions. I didn't specify it. And then after the registers, we have the instructions. For instructions, we have the instruction start index and instruction end index. Again, one last time, this is also described from the user perspective as a consumer in this video here. So that explains as well. When we decode an instruction, we get here the I type. This I type exactly relates to our definitions. And also, again, if we look at all ins.hpp, this file contains all the instruction IDs for the built-in processor modules in IDA. So the NN, as I spoke in the same video I just mentioned, designates the Intel architecture or AMD, so PC processor module. And those IDs correspond to as well their string representations and their features, as we shall see. So instruction start index, instruction end index, and then the table of instructions. So here, let me show you. So I have the PVM instructions, and these are instructions. I'll show you how I generated those instructions. So what I did for the PigletVM and the all things IDA repo, in fact, we can go to it here. And in the disassembly folder of this solution for the CTF from last month, I created that table, so I knew I wanted to reuse it for a processor module. So I designed that table in such a way where I put here the opcode and enough metadata for me to solve the CTF. But as I said, in my mind, I knew I would reuse this information. So opcode, description, and so on. So I wrote a small script that will help me generate the IDA tables quickly. So here I made a small generator script. It will generate the instructions enum while filling in the gap and also the instruction table. So that this is the most, I would say, just manual dummy work, just to put in the enums of the instructions. So these are instruction IDs. They're not the opcodes. They don't dictate anything except just a serial, just an ID, set of IDs. And then after that, we have to build the table. So we have to build the instruction table, and the instruction table, I also built it. It's a parallel array to the instructions enum. So it has to map. Index 0 should map to the instruction. Now I type 0 or instruction ID 0 is not going to be used. So I'll just put it empty. But the rest, I leveraged the generator script to generate a simple template for it. So just go over the VM spec that I copied from the solution. And I generate PVM underscore uppercase of every single instruction. So I accelerated the table generation. So I built this instruction, and if we look at the instruction here, the instruction has its string name and the features, and the features are of type prefix with CF underscore. CF, or what they used to be called canonical flags or feature flags. So let's call them just feature flags. And the feature flags that we can associate with an instruction are simple, and they're used for quick question answering. So just like to have quick understanding of the instruction. They don't dictate the full semantics. We have CF stop. We can attach to a certain instruction. CF stop will dictate that this instruction does not continue execution, stops the flow. So this could be like a halt, for example. We can annotate an instruction with a call, designating it's a call, and also a bunch of change flags, such as change operand 1, changes operand 2. So if we know the instruction, let's say move instruction that moves move destination comma source, we can say it changes 1, comma, uses 2, for example. So these are the flags. And as of recently, not long time ago, IDA now supports up to 8 operands. So the instructions, we can have more operands than usual. So let me show you the table again real quick. So here, let's go to the definition of the table. And this is the table. So what's worthwhile noting is this virtual machine jump. It's annotated with feature flag jump and uses the operand, which is jump to an address. Jump if true, it just uses the first operand, for example. Is greater or equal, uses 1. Return stops the flow. And some other instructions, I could also say use and so on, but since this is this virtual machine is stack based, the rotate and the XOR and so on, they don't use any operand. They use the stack, so that's why I used the flag 0 here. So most of those instructions that I didn't specify flags operate off the stack, so 0 operands. The ones I've set flags are not 0 operand. If we look at the PigletVM project and the tests, for example, we can see here like dupe, add, load, discard, and so on. That's the assembly syntax, and most of the stuff don't have the operand just because they rely on what was previously pushed to the stack, for example. So this is the LPH in general. So if I go back to the source code, in essence, I covered the beginning phases of developing a processor module. Flags, processor names, registers definition, a bunch of attributes, instructions. So the instruction enum, the first instruction starts at 0, and then the last one here, and then the instruction table. And the I-code, the instruction ID that is equivalent to a return or exit. So this is the instruction here, for example. And this is a reserved flag potentially used in coordination with the decompiler. But if we look at the SDK, it should show as reserved. We should not be able to use it. So here it is, unused. So this is the LPH. So what I'm gonna focus next is at how we can go further. So now that we have the instruction table, register definition, and so on, what happens next? So what happens next is the logic. Now we addressed most of the tables. Now let's have the logic. So the logic will be parts on the decoding, emulation, output, and so on. So I'll show you all the aspects of the code and how the code is organized. Now, historically, if we look at, for example, at the SDK, we will notice that there is a repeating pattern of file names in the SDK sources. Let me show you what I mean. So, for example, if I go to the IDA SDK, to the modules folder, and let's pick something, for example, arc, and what we see here is analyzer, ana.cpp, emulator, emu.cpp, ins.cpp and hpp for the instruction tables, output for the output logic, registers for the notification and so on, and register definition, processor definition, and so on. And merge, which I'm not familiar with, but this is supposed to handle IDA teams, so we can have collaboration and so on. So out of the scope for now. So you can notice that the same source files, if I take another processor module, more or less we'll have the same stuff. Analyzer, emulator, the main header file, instruction tables, teams, output handlers, and the processor definition, registers, notification. And so let's take a look at the description here. So first is the processor definition, which I spoke about. that's where we have the LPH, the processor underscore T table. We put it in the reg.cpp file. It will have the register names, their enums, potentially the assembler definition inside it, and the notification table, the handler, so the notify logic, for example. Of course, you can have your processor module not use anything at all. So you can have it in a single source file if you wish. The instruction file is where we have the instructions table and their enums. So ins.hpp will contain the enums, and the ins.cpp will contain the actual instruction definitions. So here is the ins.cpp and the table. That's it, nothing else. Then we have the ANA, which stands for analyzer, which really means the instruction decoder or the disassembler. This is where we should have the logic that handle the event that is called EV analyze. And if we look at the handler, so the way we said we can look at the handler, so we follow notify. Notify returns a new instance of a class that subclass is proc mode and overrides the on event. On event will receive the event processor EV analyze instruction. Analyze instruction is the event that should handle the instruction decoding. So historically, the logic that we implement the instruction decoding, usually we put that logic in this analyzer, analyze.cpp file. And in our case, the analyzer or the instruction decoder for the PigletVM is very, very simple. I'll talk a bit in detail about it, but its role is to get the bytes given the address and then populate the instruction object. The instruction object will then be populated in such a way that it puts the instruction type, it puts how many operands, what kind of operands, and so on. So the decoder really reads the bytes, populates a high-level instruction definition structure. As well, this is explained in this video here. That's how to consume a decoded instruction, and now we're looking at how to decode the instruction effectively. So the analyze logic has been moved to this file, and here it handles all the instruction opcodes. Once I get the bytes, I match, and depending on the opcodes, I fill in, for example, the instruction size. If it's an instruction that takes operands, I fill in, for example, it takes one operand, so operand of 0. Type here, for example, add immediate is greater or equal for an immediate. So I say, okay, the operand, which is of type op underscore t, and here we have up to 8 operands, and the opt has its type. Since PigletVM is pretty basic virtual machine, we barely have any of those. We have no operand, we don't have registers, we don't necessarily have directly memory, we have just immediate operands, and that's the beauty about this virtual machine because it's so simple. So for example, for those opcodes, the first operand is immediate, the size of the operand is a single word, and the value we also get it from past the opcode byte. So instruction address +1, we read it, and this is the value. Now get word behind the scenes knows how to read a value disregarding the endianness. So we already specified the endianness in the processor event init. I said big endian. So if I control it like this by setting this will influence the get word and so on. Get byte, of course, won't make a big difference, a single byte, but for something bigger than a byte, then the endianness will trigger. So here I'm not having to worry about the endianness since I specified it in the processor module initialization event. So the PVM store load, they take a single operand and I populated it, and I populate the instruction size. For the other operands, for the other opcodes, jump, jump if true, and so on, I specified the operand type to be near, which is a near call, since we're not dealing with segmented memory model. So everything is near. So that's how it is. So if we look at near, it's just immediate near address. The type as well, the operand size is a word. And as well, where are we jumping to? We're jumping to, we read the value after the opcode. And by design, I decided to put all the codes at a certain image base. So this is the base of all the PigletVM bytecode when I load it. This same code base is shared with the loader itself. So here the loader, when it creates the segment at the load file, as well I load the bytecode to that base. So everything has been hard-coded and rebased to this code base. So the loader and the processor module are working hand in hand. So here for handling the jump, I simply decode the operand type to be an address. That will tell IDA we're dealing with an address. And that's it. Then I specify the I type. And in my case, since it's a simple virtual machine, the instruction ID or instruction index maps with the instruction opcode. This is not going to be the case, let's say, for a more complicated instruction encoding scheme. So let's take just as well back to the PC processor module. The opcodes are arbitrary, random, they're not necessarily indices. And when we decode, we assign the instruction type, the I type, to an index, but the decoding scheme is way more complicated. In our case, the bytecode coincides, so the opcode of the instruction coincides with the I type. So it's a very simple decoding or disassembling functionality. But if we take something else, anything way more complex, PigletVM is the most simple virtual machine, which is ideal for this introduction. But let's take, for example, i51 example and look at the assemble routine, at the disassembler. And if we go all the way to the end, this is the analyze instruction. This is an instruction decoder. And the decoder logic is big. So this is the whole decoding logic. And it relies on multiple helper functions and so on. In my case, it was sufficient to be almost 100 lines and very simple single function to do the instruction decoding. But in real life, you could either implement the full decoder with its helper methods yourself, or you can rely on a third-party library to do the decoding. And then you simply adapt that decoding to IDA and populate the instruction underscore T. So back to this example, this i51 analyzer, it gets the first byte and, for example, involves multiple decoding schemes, like, okay, basic decoding, maybe a bit more complicated decoding, which maybe there's an instruction prefix and so on. So the goal really of the instruction analyzer or decoder or disassembler is to convert the bytecodes to instruction T and simplify the whole representation. So IDA doesn't care about the details of how the instruction is decoded, it just calls you, sends you a notification event, hey, EV analyze instruction, give me back an instruction T, populate it nicely in a generic way that you can use the SDK disregarding the underlying processor module and its implementation. So this concludes the decoder, instruction decoder. So if you go back to the way historically the source code is laid out, the analyzer should decode or disassemble the instruction. It should not modify the database, should not be writing anything. It has to assume it's only reading and populating an instruction structure. That's it. And we don't have to make assumptions that the instruction address, the address is an instruction address. It could be data, so the user can go to data segment and make code. So we just have an address. From the address, we get the bytes and we disassemble into an instruction underscore T object, and that's it. Doesn't have any other responsibility yet. The analyzer will definitely leverage the instruction table, so we will see it here. And the analyzer, I'm including the instruction HPP file, which have the I types, which, as we explained, is parallel to the instructions body, so the strings and their features. So that's how the instruction as well come into play. After we have disassembled the instruction, decoded it, we have the output handlers. So as well, as we can see, really logically speaking, the code base of a processor module is clearly split in multiple set of logics. So after we do the instruction decoding, if somebody calls generate disassembly text, that could be the UI. As we scroll, it wants to refresh. It will ask, hey, how can I render the instruction you decoded in the previous step? So since the analyzer will populate an instruction T, we will get another call, another event through our notify function, which is defined in the reg.cpp file. Say, hey, I want to output something. And so the out.cpp file historically is supposed to handle the output events. So we put all the output logic in the out.cpp file. So if we look at the output file as well, we have, for example, a handler to output an operand, and we receive an operand. We can decide how to output the operand based on its type. Now we don't have oreg, so that's why I can get rid of that. Immediate, we have immediate. We have near and memory. We don't have memory in the decoder, so really the output will follow the decoder. If we look back at the decoder, we have an immediate operand type and near. That's it. But since I based my work on existing source code, I didn't clean it fully, so I still have some code that is not applicable exactly in my case. So there's no harm getting rid of this because the decoder will never put an operand type of that sort. And also we don't have any registers. So, but when we are gonna output an operand, for example, if it's an immediate, we use the helper method output value and we let it do the output for us. So these are helper methods. And for output instruction, we will be called as well and say, hey, output the instruction. So first we call the helper method output mnemonic, then we output operand 0. In my case, just one operand if it's applicable. So output operand 0. Indirectly, we'll call output operand. Output operand will check if there is no operands, operand type 0, it won't do anything. So even though I'm always saying output operand 0, which is the first operand, that will be a no operation if the operand type is void, which means no operand. And then flush the output. Other output functions, for example, output segment start, how to display the segment beginning. Really, you can be as fancy as you want. This is just display stuff. But how is this logic invoked? This logic is invoked. Everything goes back to the notification. So the on event, we should handle, for example, the event analyze. That's we dispatch to the analyze function, which sits in the historical name ana.cpp. And for the output events, for example, handle events, output header, output data. I commented them out because I'm using the base functionality, so I don't need to, it's already implemented. So like use the default implementation. Seg start, I decided just for the sake of demonstration to handle that and output the segment start syntax by myself. The output instruction, this is what takes us back to the output logic here. So we always go through the notify, which is gonna go through the procmod subclass, which has the on event, which has handler for different events, including output instruction. So that's how we eventually reach this logic from the EV out instruction event. Out operand as well, it will call this function, which will end up in our output code here as well. And these are like the most basic handlers we should implement. So I'm gonna talk about them as well in details, but this covers the output part. So the output is responsible for receiving an instruction T and providing the textual representation. So you can even control the colors as you output. Here, for example, we are already printing with colored lines, for example, color string and so on, using special colors. Same for here. For example, start the color, red color, output a value, then turn off the color. So we are already using output functions with colors, for example. So the output module, the output logic, is responsible for generating the color text, essentially. And so finally, I'm gonna talk about the emulator. Okay, so the files emu.cpp and so on, or the emulator concept. What is that concept? So the emulator is just a very basic set of logic to as well do very basic instruction emulation. And so what is the scope of the instruction emulation? It's not a full semantic interpretation. And so there is no real instruction or operand tracking, backtracing, or anything of that sort. It's really very basic thing. So one of the things, for example, is stack pointer tracking. I spoke about stack pointer tracking. That is implemented in the emulation and handler. Detecting function prologue and epilogue. This happens in the emulator as well. Detecting certain compiler idioms, detecting switches, detecting function starts, uh, as well here, cross references, for example. So this is very important. The way IDA works in general is it is recursive. So the more it discovers code, the more it will add them to the analysis queue and carry on. So if we don't have an emulator code that tells IDA how to emulate certain instruction, and if we don't supplement that with giving IDA additional cross-references, and the most basic cross-reference would be the code flow cross-reference. That means the instruction flows to the next step. So IDA then the kernel will then continue disassembling, disassembling, disassembling. If we don't implement a very basic emulator logic, then IDA will disassemble a single function and not function instruction, and not necessarily automatically disassemble subsequent instructions. So at the minimum, the emulator, for example, should create a flow cross-reference to tell it to, all right, this is the next one and the next one, next one. And maybe if we encounter a conditional jump or a call, we have to as well add a cross-reference to tell the auto-analysis engine in IDA kernel to follow and recursively keep on disassembling. So part of the emulator job as well is the cross-reference creation, and that will enhance the recursive code discovery and data discovery. As well, the emulator. So the emulator is where we can keep improving the analysis in IDA. This is where we can have a very basic disassembler with no intelligence versus a disassembler, which is the analyze logic, plus some intelligence to it that makes it detect stuff. So if we want to compare to the PC processor module, for example, exception handlers, switches, prologue, epilogue, and other stuff that we take for granted, these are hard-coded rules and heuristics in the emulator part of the PC processor module and the source code. So let me show you the most minimal emulation duty. So I'm gonna open emu.cpp and show you the most basic logic. So for the emulator logic here, I kept it really minimal. As well, I'm handling the emulate. And how do we reach this code? As well, this is reached via the notify. So if we look at the on event, which is the newer version of the notify function, The emulator should be handled when we receive the event emu instruction. Then I'm calling my helper method. We can call it anything we want. And as I said, the whole logic doesn't have to be split in multiple source files. It could be in a single file. So the emulator is very simple. I receive a already populated instruction object from the analyzer phase. So the analyzer populated it. Maybe we're headless, we're not rendering. So the out component might not be involved at all until either we have a UI or somebody called generate assembly text. Otherwise, I'm decoding, then the decoder will be invoked and the emulator will eventually be invoked. We'll receive the emulate instruction event, and this is the logic. So at the minimum, we should just tell IDA to add a cross-reference from one instruction to the other with the type flow. This means this instruction flows to the next one. And that's what helps IDA automatically keep on decoding, discovering, and so on. If I omit this code, or even omit the whole emulator, we'll have to manually make code each line, each address make code, because IDA will not continue automatically making code. So by just having that minimal piece of code here, it will be able to handle the jumps, for example, with the arrows, cross-references to the jump destinations, and cross-reference from and to, all of those. The way we see them in IDA disassembly is because of the explicit calls. So here, I'm also just checking for basic instructions. So here, I take the instruction, and the only instruction that does not flow is the jump. So I turn off the flow flag here. And I'm using the canonical flags or the instruction feature flags from my table. So if I go back to my table, most of them flow except the ones I explicitly marked as stop. And so I'm leveraging that information real quick to keep my emulator generic. So, hey, give me the features. If we look at this helper method, all it does is behind the scenes go to the instruction table and get the feature which we have defined in our ins.cpp file. So these are just helper methods, but we can see how they are reading the data elements that we spend a lot of time explaining. So the emulator decide whether we have flow or not. If it's a jump, then turn off the flow, so don't create a flow cross reference. And if it's a conditional jump, I want you keep the flow, so it flows to the past the not, so the false case, for example, it flows to the false true case, and it jumps to the target of the operand. So operand 0 of address. This one, operand 0 dot address, is exactly what we populated in the disassembler. So here, those guys, we said, okay, so when we decode, this is the address where we're jumping in true, false, or direct jump. So the emulator, that's all it's doing. If it's a unconditional jump, we only add the target. That's our cross-reference of type jump near. And for flow, additionally, potentially, we also put the false true case, which is every instruction will, if it's a conditional, it has two outputs. It goes to two cases, the false true or the destination. And that's what we're doing. So if your processor module doesn't have any conditional jumps, or let's say even direct jumps, this would be what you need. That's it. Just, hey, every instruction flows to the next one. And that will help the IDA kernel to recursively keep on decoding automatically. But here we gave it a bit more intelligence. So it knows how to handle conditional jumps and create the proper cross-references. The emulator has more responsibilities, not just these responsibilities. So I kept it very simple just to augment the cross-references. But in reality, it should be doing more. So let's explore something else, for example. So let's look at the emulator here. It could be complicated. Back when I worked at Hexrays, I remember looking at the PC processor module emulator code, and it was the biggest file because it had so many facilities, detecting switches, stack pointer tracking, idiom recognition, as I said. So all of this is in emu.cpp, stack pointer tracing. So for example, let's go to the handler. So let me see, where is the emulator? So this is the emu, which will be called through the on event or the notify. And there's a complex logic. The first and the most minimal is quickly, let's do the flow just. And then if it's a call and jump, handle it. If we handle it, we'll see it might potentially also create another cross-reference. So here, for example, it's even making the operand as an offset, a direct address, adding the cross-reference to the target, for example, and specifying what kind. We might see handlers for potentially automatically creating stack variables. So here it recognizes, for example, instructions dealing with the stack pointer, and maybe it's using the stack. So hey, maybe I should automatically create a stack variable, and so then IDA will automatically, we will use here the OP stack variable to create a stack variable, for example. Different kind of things here. For example, we deduced based on the instruction we're emulating. If it's potentially data reference, we're automatically adding data cross reference. So the emulator logic is complicated, and there's so many callbacks, but the majority are optional. And because they're optional, it makes us quickly get started in the minimal functional processor module. But in reality, you want to improve on that. So for example, this example processor module implements jump pattern detection. So potentially creating a switch table. I don't know if they do here. Use the switch API. So as well, IDA SDK has like switch APIs to create switch tables and so on. Yeah, it should here. This is related to the switch creation, IDA SDK APIs and so on. So the emulator can be as complex as it can be. So let me walk through some notification events related to the notify routine. So the processor notify or on event, for example, we can have ev init. We can receive the event terminate. So processor, we are unloading the processor module. We are changing the processor module. We selected a different assembler syntax. A new file has been loaded. So we just started this assembly. An old file has been opened. A new binary file is being loaded into the database. When we say file, load additional binary. A load binary finished. We're changing the processor specific options. We are decoding an instruction, emulating output mechanisms, which we will redirect to out.cpp, for example. Output instruction, output mnemonic, output operand, output label. A segment is moving, you get notified as a processor module. Maybe you update certain cross-references, whatever you think is needed. Coagulation event, a rename event. So for example here, the rename event is what people hook to make plugins that allow you to collaborate with IDA. So they use hook to notification events, and then they receive EV rename. They can then track the rename operation. Now, what is the use to implement this in your processor module? Don't have an idea, but you can have what we call processor module extension plugin, where you can augment the functionality of an existing processor module. So maybe you can write such a thing just for the sake of tracking rename operation and dispatching them to different clients while IDA clients are collaborating. As well, you can, in your processor module, handle the isFar jump. So these are things. Let me see where they are. If it's in idp.hpp, let's see here is call, for example. So we have some functions that are generic, which we simply give an instruction object, no matter what's the underlying processor module. And this is supposed to return is true or false if the underlying processor module handles this event, which is, for example, is call, is return. If we implement it, then our processor module can work with those generic APIs. Then our processor module, we can call is call generically. We don't have to check for the opcodes or instruction IDs or itypes and so on. Just is call. If the processor module is rich enough, it handles things like is call, is return. Then we can write generic plugins that don't have to have if else. If processor ID is ARM, then let's check for the ARM instructions. If it's PC, let's check for PC call instructions or return instructions. So that's a way to make your plugin generic. So it's a good practice to implement those events as well. So if I wanted to implement the is return instruction, we can see here it takes two arguments, the flags and the instruction. So I would have to go and augment the emulator here, for example. Sorry, not the emulator, it's its own event. So here we should have, for example, in the notify, and we should respect the, so we have instruction and flags. So we take those flags and we return. So here, I'm not sure exactly what is the type of the flags. Maybe it's a regular int, so I'm gonna double check in a bit by looking at an example. So for example here, I got the arguments, and since I got the instruction, and I can consult my instruction table. So the return maybe could be the done, for example, and I think there must be a return as well. So maybe I can check for instruction type return and done. So here return, for example, instruction I type is read, then or is done, for example, and so like that I have implemented the return notification event. So since it's not fully clear, I always consult with the example. So I will look at an example implementing this event, and I can implement something similar. So we can see it implemented in different cases. So here, for example, so the flag is a character. Now, was that clear to me? Let's see here. Yeah, I missed it. So yes, it's a character, and here. So that's the gist of it, essentially. All right. So looking back at the whole picture, we covered all the necessary components, starting from the LPH, the data tables, then we transitioned to the logic, which is the notify routine. And we spoke about how the logic is distributed among different source files to handle output, decoding, emulation, and the table and the instructions, their mnemonics and flags. And finally, let me quickly talk about, just again, finalize with the part where we talk about what should the notification function handle. So at the minimum, event init for a processor module, event terminate, analyze instruction, handle the mandatory output events, implement the very basic emulator at the minimum, add the flow cross-reference, potentially implement classification events, instruction classification events such as isRet, isCall, isCondition, and as well optionally miscellaneous event. Did we create a new database? load an old database? Are we changing the processor options? And let's see, uh, maybe function. This will help potentially read the database, read some bytes and detect if it's a potential function start signature. We can also implement, for example, is indirect jump, is switch, and there's so many events here. And the more we implement, the smarter our processor module is. So as of now, I don't handle stack variables, for example. So these are the bunch of events. Even we can implement an assemble, which will complement IDA, which will let us then go and implement functionality that will be called via the menu here, patch assemble. Assemble will eventually call us by sending an event assemble, which we can handle, for example. So these are all the callbacks that we can keep implementing if we wish, for example. So now that I covered everything in the processor module, let me run it. I'm gonna run it through the loader. I'm gonna revisit quickly the loaders, and we will see how after the loader finishes and selects the processor module, the proper processor module will kick in, which is the PigletVM processor module, and we'll see this assembly. So back to my project, this Visual Studio solution is generated with CMake. So that again, that's IDA CMake. Makes it easy for me to put breakpoints and single step my code. So let me run IDA as well directly from Visual Studio. So make sure here passing the proper arguments. Okay, so my startup project here is debug, this one here. Okay, so let me change it to this one. Also, it won't make any difference since both DLLs will be loaded. Okay, so for example, for this one here, I'm gonna run the IDA development, which I put in here. And the input, I'm gonna let it find one of those PigletVM files which have been loaded with a file loader which will pick them up. Okay, so let's disassemble, run IDA and disassemble this, which will first go through the file loader logic. The file loader logic will load it into the database, select the processor, IDA loads. When IDA loads, it will pick up the proper processor by its ID since we set it. It will get its LPH. It gets the assembler table. It gets the notify. It will call it, return a proc mod instance, which we subclassed, which eventually most of the logic will be on event, and we gave it the minimum events: init, analyze, output, emulate. So here the file loader recognized. When I hit OK, the load file callback from the file loader will kick in, which now it haven't yet. So if I put breakpoint here, maybe the symbols are not correct, but anyway, I will have a breakpoint if I wish, and then it will work. And now what we see is the decompilation, or the disassembly, and that's the disassembly here. We can have graph view as applicable, and we will see, for example, the jumps. We can see the arrows, we can see the cross references here. Here cross reference, jump, and the graph view. Since we are in a function, I can change representations. For example, here I can press R. We can see, so if you look at the CTF solution, which is here, and you will, I have already decompiled the logic. So this is fine, but it's not very comprehensible. So in the previous, in the solution, one of the previous videos, I convert this to x86 and then decompile it with the x6, the PC decompiler. but this is it. I can add comments. And you see, for example, this symbol here, why the comment looks like this, not as a semicolon, is, as we said, it has to do with my assemble table. So if we look back at the assemble definition, for example, the comment is this character here. That's why we see it like that. The dot byte for uninitialized, for example, here I have created the memory segment, which is BSS uninitialized. We see it like that. The string here dot section memory BSS, this is also based on my output logic here for output segment. So output segment start, this is how I chose to display it. Dot section, the segment name, and the class here, for example. This is the logic. Section code, this is the logic here. Displaying dot section code, you can change it anyhow you want. So if you plan to reassemble, if you plan to save file, produce, create assembly file, which will generate a listing like that. If you plan to reassemble, then you have to focus on making your assembler table more correct so it can be consumed quickly by an assembler. Okay, and so here pressing H for decimal, not decimal. If this virtual machine has more complicated logic, multiple functions, so PVM is no functions, just a single piece of block. So no function call opcodes, just execute row bytes, and that's it. And the only control flow is return and unconditional jumps and conditional jumps. That's it. So yeah, and then return. Alright, so let's recap. This was a lengthy video. I described the mechanics of building a processor module and how the whole logic transitions from the data table, starting with the processor definition, the LPH symbol, all the necessary tables between the registers table, instructions table, instruction mnemonics, and the necessary flags. And then I spoke about the notification routine and subclassing a proc mode to handle essential events such as the output logic, instruction decoding logic, instruction emulation logic. And finally, I demoed the whole thing and put the whole project in perspective, starting from the file loader all the way to the disassembly, emulation, and the display on the screen. All right, thank you, and I'll see you next time.